Hello, this is our report on Flexure and Strain Lab by Mario Russo.
G. Jimmerwala.
And so, Kazi.
So the main purpose of this lab is to use the strain gauge, and with the use of strain gauge, we were able to determine the elastic modulus and stress, and all of that was done by putting all the data we got from the strain gauge into multiple bending equations, and after that, we were able to plot different comparison graphs, such as the force versus displacement graph and stress versus strain graph. So you may ask, what is a strain gauge? A strain gauge is a sensor that pretty much measures strain upon bending. And um, the reading we get from a strain gauge is called the strain voltage. So how did we conduct this lab? So pretty much for the procedure of this lab, we had this thin polycarbonate beam and we put the strain gauge, which is a tiny sensor in the middle of the beam. And when you bend it, we were able to get a reading through a multimeter. So the first part of the lab, we had this semicircle, foam semicircle. We put the beam on top of it and we bent it. And whatever reading we got, we put it into bending equations and in our Excel data sheet. The second part of the lab, we were able to measure the strain by applying 3-point bending using a tensile tester. And after that, we were able to put all our data into an Excel sheet and make our graphs. Now, Mario will show us what the data looked like.
So, as G just prefaced, for the first part of the experiment with the strain gauge in the dead center of the sample, in order to, because that is the point with the maximum displacement, we were able to calculate strain three separate times, with the average being 0.007262, and that had a 26.74% error, relatively, not perfectly accurate, but still within reasonable realm. And then in the second part of the data, using the measurements of the sample itself and the force versus displacement data, which was initially in pounds force and inches, which we then converted to newtons and millimeters, so it would be easier to work with. We were able to calculate the moment about the z-axis, the stress and the strain, the elastic modulus at different force and displacement values, along with the vertical displacement along different points of the X position along the beam when under 3-point bending testing. Now, the data in these graphs can be shown here. For force versus displacement, it's a linear proportion, as would be expected. And the stress strain, again, more linear than would be expected for a normal stress strain. But the reason this happens is because this is all elastic deformation. The second we took the force off, it immediately returned back to its normal shape. So it never reaches plastic deformation. And the slopes of these two graphs show the elastic modulus for the sample. And then here on the right, we have the shown deformation of the beam when under 3-point bending for the left half of the beam because of the way the equation is set up. You can see it's the general shape of a bended beam as under 3-point bending. Now, the values we calculated from the strain gauge stress strain graph, the slope there gave us a value of 1.018 gigapascals, which had a 59% error from the reference value from MatWeb of range between 1.79 and 3.24 gigapascals. Then also the elastic modulus by a displacement at different at all the different values of force and displacement gave us a value of 5.003 gigapascals, which was a 99% error, but that wasn't one of the main values we used. That was just all of the values summed together and found the average. And lastly, the elastic modulus from the stress strain graph slope gave us a value of 3.576 gigapascals, just outside of the range expected from MatWeb.
From this experiment, we learned how to test for deformation of a beam under load. And upon further analysis of the data collected from the experiment, we learned how to mathematically represent the deformation of a beam under load. And we also learned how we can predict the deformation of a beam-like structure under a load using the known variables and plug them into the equation. In summary, the data derived from the experiment accurately syncs up with the mathematical representation of this problem. The equations represent the cause and effect of it. The equations represent the cause and effect as a mathematical function.
So the one of the issues that we ran into was the multimeter readings. It was very unstable. Either it was rapidly moving up or rapidly moving down. So I think in the future, if we're able to get a multimeter that's more stable, we'll get more stable readings. And future recommendations for people who are conducting this lab would be sanding the sides of the polycarbonate beam. So when you're doing the 3-point tester, for 3-point tensile tester, it doesn't slip. And also when applying the force, yes, there's 100 lb force limit, but just go slow for more better and accurate data.
Here we have the references of the known MATWEB value for the Young's modulus, which was found online and a trusted value to compare our calculations with. And the rest of the references are provided from the lab manual, just general data about 3-point bending testing and the sample used.
So some of the questions were, does the shape of the curve match the deformed beam observed during the test? And why is it only the left half of the beam shown? So as we can see, when the equation is represented graphically, it also visually represents the deformation of the beam under load. And as Mario explained earlier, this equation only correlates to the left half of the beam.
That's correct. If you wanted to show the right half of the beam, to calculate those points at least of deformation, you would have to use a separate equation, which we were not told to do. Or you could simply mirror the deformation up to the first left half and the displacement along the y-axis to get the right half, because it would be a symmetrical bending. This is the end of our presentation. Thank you.